Our next speaker is Vickie Kloeris, who Washington Post calls NASA's top chef. In her current position as manager of the International Space Station Food Systems, she is responsible for keeping our astronauts well-fed as they explore through space. She is an active member of the Institute of Food Technologists and currently serves on the Advisory Council for the Institute of Food Science and Engineering at Texas A&M University. Thank you, Vickie.
Yeah. Okay, so can everybody hear me? I'm wired, so I don't have to handhold one. Yeah. Okay, my name is Vickie Kloeris, and just to let you know, I'm a food scientist by training. Undergrad, I was a microbiology major at Texas A&M, and as a senior, I took an elective in food microbiology, and I got very interested in the application of microbiology to the processing and preservation of food. So I went on to get my master's in food science and technology at Texas A&M. And I didn't really, at the time, think about an application for the aerospace industry for NASA. I actually grew up right down the road from here in Texas City, Texas, but didn't really think about food science in terms of NASA. Typically, food scientists work in the food industry. They do like product development for food companies, or they do quality assurance, or they work for the FDA and help with regulatory inspections or with writing regulations for the food industry. So that's kind of where I envisioned I would be going and with my career. And then I came to Houston, and the first job I had was doing quality assurance for the Memorial Hospital System here in Houston. They had a food plant where they made food for about 6 hospitals in the region. And so they hired me to do quality assurance for them. And so while I was working there, I started going to the local meetings of the Institute of Food Technologists, or IFT for short. IFT is a headquarters professional organization for food scientists. It's headquartered out of Chicago, but they have regional sections. And so they had a regional section here in Houston that held monthly meetings. And so I started going to the meetings and hearing some of the technical speakers, and I met some of the folks who were working down here on space food. And I immediately thought that has got to be the coolest job that a food scientist could ever do, is to work on the food system for the space station. And about 2 years later, so I kept going to the meetings. About 2 years later, I got a call from one of the managers down here, and he said, "We have an opening. Would you be interested in interviewing?" And I'm like, "You bet I would." And so I came down and interviewed, and I came to work here in August of 1985. So I came to work, 16 shuttle missions had flown prior to my arrival. So of the 135 shuttle missions, I worked on all but the first 16. And so I actually spent a lot of time managing the shuttle food system. And then I transitioned over to space station, and we finally brought on a second food scientist to help with managing the shuttle food system, because both together actually was really too much for one person. We also have a component in our lab here where it's called our Advanced Food Technology Program, and we do research on food for exploration class missions, so for like that first trip to Mars. So we're working on some of that as well. So what I'm going to do is cover a little bit about the history of space food real quickly, and then I'll go into the current food system. And I hope to do this fairly quickly, and so there'll be a little time for Q&A. Cubes and tubes. Most people, this is what they've heard about space food, and this was the earliest space food, Mercury and Gemini program back in the 60s. The cubes were dried cubes that were coated with an edible film, a starch, to keep them from producing crumbs. The engineers were just absolutely paranoid about crumbs getting loose in the cabin on those early missions. And so cubes coated with the film, and then tubed foods, basically baby food, pureed tubes food in a tube that they just squeezed into their mouths. So this food, like I said, was for Mercury and Gemini. It transitioned into the Apollo program, so some of it was used in Apollo as well. And it did provide the nutrition that the crew members needed, but it certainly wasn't very aesthetically pleasing as far as satisfying the psychological aspects of food. During Apollo, they added what was called the spoon bowl. Spoon bowl was the first package, the first food items that actually allowed them to use a utensil, a spoon. So what they had was this adapter that you see here was actually where they injected the water. These were all freeze-dried items in the spoon bowl. They injected the water using a handheld water gun, and then they cut the top of the package open and ate out of the package with a spoon. So that, prior to that, everything had either been squeezed or popped into the mouth. So utensils were added during Apollo, and then we went to Skylab. Skylab, does everybody know what Skylab was? Skylab was our the first, you tell me back there. Yes, it was the first U.S. space station. It was up in the mid-'70s, that's correct. And since, I just had to ask, since it was before most of you guys were born. But Skylab was actually the most sophisticated food system that NASA's ever flown because it included some frozen and refrigerated foods. So this tray that you see here served both as their meal tray, but it was also the oven. These front three wells were controlled by these switches. They put the frozen or refrigerated items in there, flipped the switches, and these were on a timer, and that's how they heated their frozen and refrigerated food that needed heating prior to consumption. So that was Skylab. Then we went into the shuttle era. Okay, so in the Skylab flew in the mid-'70s. In the late '70s, they were designing the food system for shuttle. Shuttle first flew in 1981, so in the early '80s was the first flight. So in the late '70s, they were working on the food system, and a conscious decision was made that they were going to use as much commercial off-the-shelf food as possible to save money. Prior to that, practically everything they sent into orbit had been custom made to go into space. And so by using commercial off-the-shelf, they could save money, and so they went to a lot of commercial off-the-shelf items, and they also went back to a shelf-stable food system because the shuttle was considered a work vehicle. It didn't have enough power to support refrigerators or freezers for food, and so we were back to an all shelf-stable food system. The first shuttle packaging system, we had thermostabilized foods. These are your canned foods, except we used some commercial cans, but we also used pouches. It's called a flexible can. This is a technology that was developed by the military for the meals ready to eat, the MREs, which is their primary ration system food system for the troops out in the field. So this is just like a canned product. It's ready to eat, except it's in a pouch, and it weighs a lot less in a pouch, so we like it for the same reason. So we continue to use a lot of thermostabilized pouch products. Early on, we had these rigid containers for our rehydratable foods and our beverages. The beverage, this container had a septum in the corner that you see here that allowed the injection of water on orbit. And for the beverages, they used this straw to insert through that septum and drink out of the package. This worked well when the shuttle flights were short and there weren't many crew members on board. But as the flights got longer and the crew size went from 2 to 5 to 7 to at one point we actually had 8 on a couple of flights, these packages just took up way too much room in the trash. So after the Challenger accident, one of the things that we did during that downtime was to come up with a new design for these 2 rigid packages. And this is what our packaging engineer came up with for the beverages. So this is a foil pouch. All of our beverages are in powdered form. We use commercial powdered beverages, so we still use Tang. We use Country Time lemonade. We use instant teas, instant coffees, so all in powdered form. We package them in these pouches. This white adapter that you see at the top was designed to hold that same septum that was in the corner of that original package. So the septum is inside, the water is injected through the septum using, they call it a rehydration station, but basically it's a needle that measures water. And so they dispense the water in there using the needle, and then when they withdraw, that septum closes off. It serves as a little plastic one-way valve to prevent the water from flowing out of the package in microgravity. So to drink, they insert that same straw. The straw has a rigid tip. It holds that septum open so that the fluid can flow out of the package, and then they have a clamp on the straw so that in between sips they can clamp it closed. If you left this open on orbit, it wouldn't happen quickly, but gradually the fluid would flow up the straw and out of the package, and that could create a really big mess. So we replaced our rigid package for beverages with the package you see here, and we replaced the rehydratable package for the freeze-dried foods with the package that you see here. So it has the same septum adapter in the top. They inject the water. In this case, the label, it always tells them how much water to add and about how long they need to wait before the product will be fully rehydrated. Once the product is fully rehydrated, they can cut the package open and eat out of the package with a fork or spoon. Typically what they'll do is they'll cut an X across the top here. They'll eat out of the center of the X, and the flaps of the remaining material help hold the rest of the food in the package while you extract the bite out of the center. You're depending on the surface tension of the wet food to cause it to either stick to your utensil or stick to the package. So they can't put real huge bites, they have to kind of take smaller bites. They put too much on the utensil, there won't be adequate surface tension to hold it in place, and it'll fly off. So they learn pretty quickly how to manage that in microgravity. I mentioned the thermostabilized foods. When I first started here, we were buying MREs from the same vendors who make them for the military, and we were flying those as our thermostabilized pouched entrees. And that worked well until we started going into long duration space flight. The problem with the MREs for us is they're way too high in salt and fat for what we want for our crew members. So the Army, the typical customer that the Army is feeding is a 19 to 21-year-old soldier. They need the extra fat in there to boost the calories up, get the high enough caloric content, and the soldiers are doing maneuvers, they're sweating a lot, out in the desert, so they need the salt to replenish electrolytes. Well, our typical customer is a 40-something to 50-something-year-old astronaut. We don't want that extra fat in there because they don't need that. And the high sodium is a problem from a health perspective for microgravity. We have a couple of health issues that show up in our astronauts on orbit that, while they're not caused by sodium, they can certainly be made worse by sodium. One of those is bone loss. We've known for a long, long time that when astronauts go into microgravity, they begin to experience bone loss. All of us turn over our bone. Our bone is a living organism or a living tissue. So you're constantly breaking up, building up bone and breaking down bone. When you go into microgravity, for some reason that gets out of kilter and the breakdown side of the equation becomes too much. And so they're actually losing bone mass. And so they can try to offset that with exercise and diet, but we know that high salt makes bone loss worse. And so that's one of the reasons that we wanted to try to reduce the sodium in the diet. Now, for the longest time, we didn't raise that as a huge red flag because when they come back, they get that bone mass back. It takes about twice as long as they're on orbit, so if they're up there for 2 months, it's going to take them 4 months to get it all back, but they get it back. But then, when we went to space station and we started staying on space station, and now we've been up there for 12 solid years, we've had crew members, more than 12 years now, we've had crew members on space station, they started seeing an additional issue, not in all the crew members, not like the bone loss where everybody had that problem, but a few crew members, they were seeing increased intracranial pressure. The way that it was manifesting itself was as vision changes in the astronauts. And so some of the astronauts were, they were losing visual acuity while they were on orbit. And they figured out over time that this was because of this increased pressure that was putting pressure on the optic nerve. And the bad thing is they don't recover that when they come back. And so for that became a huge red flag for our flight surgeons because, doctors take the Hippocratic oath, I will do no harm to my patient. And so they don't want to knowingly cause permanent changes in the astronauts. So right now that's a huge health issue for, I work in the Life Sciences Directorate, and that's a huge health issue for us, is how to solve this intracranial pressure issue. So we were directed to reduce the sodium. We just finished a 2.5-year project to try to bring sodium down as much as we could in our food system. It's hard without refrigerators and freezers because salt is a preservative. But we were able to reduce it significantly. And in order to do that, we started making our own thermostabilized foods. So we actually started that before this whole intracranial pressure came up, but now we're having to do even more of that because the MREs, like I said, are way too high in salt. And so our food scientists in the lab here have come up with about 60 formulations of thermostabilized products that we make on a regular basis for the space station. We also send some intermediate moisture foods. These are like dried fruit, dried beef. These are commercial products that we repackage to send to orbit. Natural form foods, again, these are all commercial off-the-shelf products. They fly in their natural form, meaning all we do is repackage them. So these are cookies, candies, nuts, crackers, things like that we buy. There's a couple of reasons we repackage. One is because all the materials that go in a spacecraft have to be tested for flammability and off-gassing. So it saves a lot of money to put them in a pre-approved, pre-tested material rather than trying to test all the different manufacturers' packages. And then every time they change something about their packaging, we'd have to go back and retest it. It also allows us to put them in single serving, which helps. It's difficult to eat from a bulk package on orbit because everything like this is going to tend to float out. Excuse me. So single serving helps, and it also allows us to vacuum package, which reduces the volume. And it also, in the vacuum packaging process, we can remove a lot of the oxygen, which will help extend the shelf life of the products. We have a few irradiated meat products where they're just like the canned products, but instead of using thermostabilization, instead of using heat to make them shelf stable, they are actually, we actually use cobalt source, and they're exposed to gamma rays to make them shelf stable. So we have about 9 meat products that we use in the food system that are irradiated. We also send a variety of condiments. Typically we use the restaurant style, just like you get in the fast food stores, but the salt and pepper has to be in liquid form. Can't use powdered stuff on orbit. So the salt is dissolved in water, the pepper is dissolved in a food grade oil similar to a cooking oil. It's in a dropper bottle, so they squeeze a drop, stir it in, and interestingly enough, when we got mandated to reduce the sodium, the first thing we suggested was, we'll take away the salt shaker. And the answer came back, no, we are not going to mandate a reduced sodium diet because not all of our crew members have this issue. So the salt is still available for those crew members who want to add it back to the products that we have reformulated. Now I will tell you, one of the goals that we had to reformulate about 90 different products in our food system. We have approximately 200 foods and beverages that we produce on a regular basis to send to space station. And of those, about 90 had to be reformulated in order to get the sodium down. And one of our goals was to try to make them taste good enough that they wouldn't reach for the salt shaker, that they wouldn't really miss the salt. And I would say we accomplished that The advantage that we have over the food industry is that we're making very small quantities. So when we take some of the salt out, and again, we're not taking all the salt out, but when we take some of the salt out, we can replace it with more expensive herbs and spices that will recoup flavor and still make the product taste good. Now for the food industry, that's really difficult because they're making, hundreds of thousands of product, of servings. We're making 200 a year. So we can afford the more expensive items. Salt for them is a cheap way to make things taste good. So that's why so many of your processed foods that you buy in the grocery store and the foods you get in the restaurant are high in salt, because it does make things taste good. And the American palate has been trained to like salty things. But sodium is way too high in our diets, in the average diet on the ground. And it's definitely even higher for our crew members on orbit because you and I get we have access to fresh fruits and fresh vegetables and salads all the time. So that stuff has no salt in it, or little to no salt in it. So overall, that helps us bring down the sodium content of our diet. Well, our crew members on orbit don't have that available to them. They rarely get fresh foods. So that's another reason. They're eating all processed, and so that's another reason their sodium is so high. So it was important for us to try to bring it down. We do provide metal utensils that they clean with wipes on orbit, but we do give each person their own kit because we have no way to actually, there's no dishwasher, there's no sink, so you can't truly sanitize these utensils on orbit. About the best they can do is use a wipe on them, and so that's why we give them their own personal kits so they're not sharing utensils on orbit. We used to have to fly a can opener, but now fortunately on the U.S. side, the few cans that we do fly, and we don't fly hardly any anymore, they're flip top. But interestingly enough, our Russian counterparts who provide food for 3 of the crew members on space station, and we provide food for the other 3, they still have lots of cans that aren't flip top. So they do have to have some kind of can opener on orbit. Now we have sent them something that's a little more sophisticated than this. This is actually, it's nicknamed the John Wayne, and it's actually what the soldiers would carry on their dog tags so that they would have a can opener with them. It does open cans, but it's slow as can be, and it creates very jagged, sharp edges. So not something you really want to be using on orbit. Now, space station, it's a picture of the International Space Station. When we first started on space station, we were sending food in containers like this. And the reason we were doing that is because they were doing all their dining in the service module, which is a Russian component of the space station. This picture was actually taken in the service module on Mir. Mir, as you recall, was the Russian space station, and we actually sent, prior to building the International Space Station, we sent our crew members, so say from 94 to like 97, 98, I can't remember exactly, we were sending our crew members to stay with the Russians on their space station, on Mir. And so they had a service module on Mir, and the service module included a rehydration station up here on the wall, and it actually had a dining table that folded out of the wall. And so for International Space Station, when we first started, the only food preparation area was in the service module. And so it looks exactly like this because the Russians basically just built an identical service module to the one they had on Mir and put that up for space station. And next to that table was this stowage area that stowed these metal containers, and that's why we were using those early on to put our food, to send our food to orbit, because it would fit in this case next to the table. Now, however, when they went to Crew of 6, they added a second food preparation area in the U.S. lab, and so we no longer had a container or a case with those boxes. So we switched away from the boxes, and we basically took the same volume of food that was in one of those boxes. Oops, did that wrong. And we packed it in this, what we call a bulk overwrap bag. The advantage to this is that it weighs less than that metal container. And so when we launch it, when we haven't launching a lot of food, we're saving a lot of up mass. It's very expensive to launch mass into orbit, so the more we can save, the better. Now, we pack our food, we pack it in what we call pantry style, so we pack all the meats together, all the veggies together, and then they go and select their meals, what they feel like for that day. So that we have a menu that we pack to, but they don't have to eat it in that order. They can eat it in whatever order they want. We do pack, sometimes when they participate in experiments, they'll have to be, for a few days, they'll have to be on a definite diet. They can't deviate from it at all. And so we pack special containers. This was actually for Mike Fink, and he was participating in an experiment that had the acronym SOLO, and it was an ESA experiment, and it was related to sodium content in the diet. And so there's just this is a half CTB. This would contain 5 days of food for him. And that's what it looks like when it's open. And the menu would be at the top so he could see exactly what he needed to eat on each day. When they added the second food preparation area, they also included a table in the node. They actually took a piece of that table that was in the service module. Early on, it folded out of the wall in 3 pieces. Early on, they decided that third section just stuck out too far. I think Expedition 2 or 3 maybe. They cut it off. And so they intended to trash it. And what they found out was it would not fit through the hatch of the Progress. And the Progress is their giant trash can. So they had no way to get rid of this thing. It was hanging around the station because it was too big to put it in to trash it. And so when we added the second food preparation area, we had a very ingenious crew that took that piece and created another table at the second food preparation area. So what you see here is them dining at the table in the node on the U.S. side. This is just a picture of what a Russian beverage package looks like. Again, this is a close-up, or shows the rehydration station in the service module. Another picture of the rehydration station. This is actually the rehydration station on the shuttle, but the rehydration station that we have in the U.S. node looks pretty much like this. For some reason, I couldn't find that I had a picture of the new one, but it looks a whole lot like this. There's a needle permanently mounted at the back. They dial up the amount of water they want, put the package in there and shove it in, and it automatically injects the quantity and temperature of water that they've selected. On Space Station, they have hot water and ambient water. On Shuttle, we did have chilled water, so they could have a chilled beverage, but they didn't have that on ISS, on the Space Station, until they added the second food preparation area. And with that second galley, they actually included a small chiller where they could chill beverages. It's very small. It's about the volume of your home microwave. And so it's not really big enough to refrigerate a bunch of stuff, but it does allow them to prepare a beverage before they exercise, put it in there, and then they can have a cold drink or a chilled drink after they exercise, which they really like because they have to exercise a lot every day. We don't have an oven on station, so what we have is this, it's called a food warmer. It's kind of a metal briefcase. It's got a hot plate in the middle and on both sides, so underneath here there are cavities where those pouches get loaded in. They close it up and plug it in. In about 20 minutes they've got hot food. Now the Russians in the service module on their table, they have slots where their cans go. But those slots are only sized for their cans, and so we had to come up with something for our pouches, and this is what we came up with. This just shows, this is a rehydrated, this was split pea soup, and it shows you how it has to be thick so that it will stay when they're trying to eat it, stay in the package and stay on the utensil. Tortillas are very popular. They're the most popular bread product we have on orbit because they don't create a lot of crumbs. So that's basically it. I'm going to stop there, and if you have questions, I will be glad to answer your questions. And I also have samples up here that you can come and look at. So, any questions that you want to ask for the whole group to hear, or you can come up and ask me individually, either way.
I have a microphone so I can hand it out.
Oh, okay. You dropped something there. Oops.
I have a question. Were microwaves ever used on any of the space stations Were microwaves ever used in the space stations in any major way in any like food designing processes or no?
No, we actually, originally, I didn't really go into this because short on time, but originally the International Space Station was going to have what was called a U.S. habitation module that was going to include refrigerators and freezers for food. In the late 90s, probably 96, 97-ish, it got canceled. Budget was one reason, but another was power. They quickly figured out they did not have enough power from the solar arrays to be able to run refrigerators, because we were talking about, maybe a third of the food system being refrigerated or frozen. Just could not handle that. But during the time when we thought that was going to happen, we did have the engineers here working on how they would do a microwave on orbit. The problem with a microwave, and they talked about this for shuttle too, the problem with a microwave is that you have to shield it so much to keep it from interfering with the electromagnetic interference, to keep it from interfering with the other electrical equipment and the communication equipment on board. By the time you shield it, it weighs so dang much that it's just not a viable solution. The other problem is, even though over the long haul, a microwave uses less power, it actually, when you first turn it on, it does a big power spike, and that's a problem because, like the shuttle, we couldn't have one there because it couldn't handle that. And so, yeah, they pretty much decided that microwaves just weren't a really good option for ISS, or early on for the shuttle, either one. So we've always had basically a convection type heater, a hot plate with a fan that blows warm air around. And then we've had hot water to put in the food, so that helps, for the freeze dried, that helps heat it up by adding the hot water. Way in the back.
So you may remember the other night I mentioned to you that Pete flew Skylab, and he had also flown Gemini and Apollo, so he had eaten Spam in a can and tube stuff and all that yucky stuff and Tang and everything. So in Skylab, they had figured out that it took 6 days for food to completely cycle through the body. So they had 6 different menus. And they would get up in the morning and begin their routine by taking their food out of the freezer. And they had particular menus per day. And he thought he was, at the Ritz because it was lobster Newburgh and all these amazing things. So it was a really fantastic adventure in Skylab. And is that really still the case? I mean, do we still cycle food every 6 days? It takes 6 days to fully cycle through our bodies? So what I eat today is a week later kind of gone, theoretically?
I'm not sure. They were doing, I can tell you on Skylab, I don't know the details of what you're talking about.
Oh, okay.
But I can tell you that on Skylab, they were doing metabolic experiments.
Right.
So the 6 days may come from the fact that they were trying to trace certain nutrients throughout the body.
Yeah, maybe that's what he meant by cycling through the body.
Yeah, I'm not sure. I mean, I don't think food in general takes 6 days to cycle through your body. I think they were looking at possibly, what I'm guessing based on what I heard, because this is the first I've heard of the 6-day thing.
Okay.
I think it's related to the metabolic
Metabolics?
experiments they were doing in trying to look at certain nutrients.
Okay, that makes me feel better because I've thought about that for a really long time.
But I can tell you,
the guilty trip goes for 6 days.
we have, we provide, basically they cycle through our menu about every 7 to 9 days. Basically, we provide some of all the foods that we have, And it takes them about 7 to 9 days before they have to open the next
Right.
set.
Right.
And we provide that 3 persons worth. The Russians provide 3 persons worth, but then they can share it in any manner they want to. We don't dictate to them that Russians have to eat Russian food, and they
Right,
share it.
right, right.
And then when we have ESA crew members, European Space Agency or JAXA, there's always a lot of special food that goes to orbit when ESA or JAXA is on board. And even
Right.
for Chris Hatfield, who's CSA, Canada, they sent quite a lot of special food for him. So even though we have a standard list of what we send, they get to augment that with what we call bonus containers. And in the bonus container, so for a 6-month stay, you get 9 bonus containers. And those bonus containers are basically the size of that bulk overwrap bag I showed you. And so they get 9 of those. They can put more of our stuff in there, or they can also include commercial items, as long as those items don't require refrigeration, they meet our shelf life and our microbiological requirements. They can include their favorite cookie, cracker, candy. They can even go down, now you've got pouched items in the store, like you can find Indian cuisine, you can find other cuisines that are in shelf-stable pouches in stores. And so they can include those type of items in their bonus containers as well.
Yeah, so we've come a long way from cubes
yeah.
of food.
Absolutely. I can remember several years ago, before the Apollo 13 movie came out, Jim Lovell came to our lab with some of the current astronauts, and so we did a space food breakfast for them, and he was sitting there eating, and it was so funny because he was like, oh, this stuff is great, because the food system had come such a long way from Apollo to shuttle to that point. And 2 of the current astronauts were sitting across from him looking at him like, are you nuts? Because they didn't think it was so great, but he knew what it had been before, and so he thought we had really come a long way, and we've come quite a bit further since that. So
I don't want to interrupt the kids if they have questions, but I would also like to ask one more, if I may.
sure.
Food doesn't taste very much in space. Is that true?
Well, anecdotally, we know that a lot of crew members report that they feel like their taste buds are somewhat dulled in space. Okay, we don't really have scientific data to say why that happens, but we do have some pretty good theories about why that happens. Most of the way that we perceive the taste of the food, a big portion of that is the aroma that we get from the food. And the easy way to prove that is when you get a cold, things taste really bad because you're all stuffed up. It tastes like nothing. It tastes like cardboard because you can't smell it. And so when our crew members go into orbit, they have some of those same issues. So early on, especially in space flight, the fluid shift occurs, and so they're all congested to begin with. And that congestion lasts for a while. And so it's just like having a cold, and things are going to not taste, as good to them. But over time, like on shuttle, that was a big issue because the flights were short, and so a lot of times that stuffiness never really went away for the shuttle crew members. But on space station, they're up there for 6 months, and so over time, that part of it goes away. But you also have to take into account that they're eating out of packages rather than off a plate, so that inhibits how much aroma they're getting from the food. They're also in an enclosed environment with a lot of other odors, some of which aren't necessarily pleasant. So there's a lot of competing odors that are detracting from the aroma they're getting from the food. And in microgravity, heat doesn't necessarily rise. So when you have something that's hot, like hot food, the heat coming off of it, the aroma and the vapors coming off of it, aren't necessarily going to rise automatically to your nose like they do here. In microgravity, they tend to dissipate, and they can dissipate in other directions. So all of that taken together, it is not incredibly surprising that they feel like their taste buds are dulled, that they're not getting as much. So because of that, the hot sauces and the salsas and things like that are pretty darn popular. Our most popular item historically has been our freeze-dried shrimp cocktail because it has horseradish in the sauce, and so it's got a nice little kick to it, and so they really like that on orbit because it taste jazzier than some of the other stuff that they're eating.
All right, time for one more question.
Got one at the back. And again, I'll stay here afterwards if you want to come up and ask other stuff.
Has there ever been like any big any ISS experiment on like foods, like space food or something?
Well, we've actually had a couple of nutrition-based experiments. One was on the International Space Station. They've had more than one. Early on, they did an experiment. They're always very concerned about renal stones. And so they did an experiment on looking at how being on space station, does it increase your risk of having kidney stone? And so when they were doing that experiment, the diet had to be not controlled, but it had to be monitored. They had to know exactly everything they were eating. And so we have barcodes on all of our food packages, and if you come up, you will see that there's barcodes on all these. And so whenever they participate in an experiment where they have to log what they're eating, they're going to use a barcode reader to do that, and it will automatically log that for them. So we were involved, the food was heavily involved in the renal stone experiment. It's also involved in that, or was involved, they finished that solo experiment that I told you about, which was a European Space Agency experiment. There's another project, another nutrition project going on right now. It's called Pro-K for short. And this is an experiment where they're looking at if you have a diet that's higher in protein from plants, if you decrease your animal protein, increase your plant protein, will it lessen bone loss? So that's the basis of the experiment. So they're putting some of them on they put them part of the time on a high plant protein diet. Still has some animal protein in it, but way less than they typically eat. And then they compare that to a high, so they've got low and high versions. And so they're collecting data on that, and that's still underway, so they don't have the results from that. And then actually the European Space Agency is starting another experiment that's related to nutrition. And it's actually an experiment, it's called Energy. And it's to look at what their actual caloric requirements are. Now on shuttle, an experiment was done on the US side where they used an isotope of water. It's called a doubly labeled water experiment, and this is used in nutrition research on the ground. It's an acknowledged way, and what happens is you ingest an isotope of water, and by tracing that isotope through your body, and basically they see it come out in your urine, they can back calculate and figure out exactly how many kilocalories, how much energy you're breaking down in your body. And so we did that on shuttle. The nutritional biochemistry lab did, and all the data we collected on shuttle indicated that there was no significant difference between the caloric requirements on orbit and the caloric requirements on the ground. But shuttle was short duration. And so it is a very good idea that ESA is repeating this experiment on long duration crew members, because if you're on orbit for 6 months, it may be that if the calorie requirement is less, that will show up over time as your body adjusts to microgravity for being there for a long time. So we should get some data. It'll be a while before they just started this experiment, and they like to get 16 test subjects, a minimum usually of 16, before they start trying to draw any conclusions from the data. So that's going to take quite a while before they get there. But it'll be very interesting to see if they show any difference in these long duration crew members as far as caloric requirements.
All right, well, thank you so much. I think Vickie's going to stay if you have any additional questions. And speaking of food, the pizza is ready. So if you go outside to the pavilion, I believe the game trucks are here, as well as 300 cake balls, which is a Texas tradition. So, all right, well, thank you so much.
You're welcome.